demonstrate Hall effect experiment. This is very important experiment, fundamental experiment, and as I demonstrated that using this effect, Hall effect, we have devised uh, for magnetic measurement, for magnetic field measurement. We use Hall probe, Gauss meter. So uh, today I will demonstrate the Hall effect experiment to find out different parameters of metal and semiconductor. So if I give you a semiconductor, you know these semiconductors are three types. One is intrinsic semiconductor, means number of concentration of hole and concentration of electrons are same, that is in semiconductor, that is intrinsic semiconductor, and other type is extrinsic semiconductor. If that intrinsic semiconductor is doped with uh, trivalent or pentavalent atoms, then you can get N-type semiconductor or P-type semiconductor. So now, if I give you a semiconductor, so whether it is P-type semiconductor or N-type semiconductor, how you will tell? What is the carrier density of that semiconductor or metal? What is the carrier density? How you will find out? How you will find out the mobility in semiconductor? You know this mobility is very important parameter. How you will measure the uh, mobility of carriers in semiconductor? So Hall effect experiment is the experiment which can measure the carrier concentration in metal or P-type semiconductor or N-type semiconductor. It can tell the type of semiconductor, whether it is N-type semiconductor or P-type semiconductor. And we can measure the uh, mobility of carrier from this experiment in combination of the resistivity measurement or resistance measurement. As I have one experiment how to measure the uh, resistance or resistivity using the Bluetooth method. So either this resistivity or conductivity of this uh, semiconductor will be supplied, or you can measure the resistivity of the sample, and then if you do this whole experiment on the sample, then you can find out the mobility. So type of carrier, carrier density, mobility of carrier in semiconductor, those parameters you can find out from this experiment. So we know this Hall effect basically, if you have a sample, say you have your shape sample, so this is x-axis, this is x direction, this is y direction, and this one is z direction. Sorry, this I think I have a mistake. So this will be z, and this will be y direction. So, uh, so if current flows, constant current flows along the x direction I, And if magnetic field is applied along the z direction, then there will be voltage or electric field will develop along the y direction. So then that electric field or voltage is called Hall voltage. So this Hall voltage is basically depends on the some constant RH is called Hall coefficient, and this current along the x direction I have written Ix and Hh. This applied magnetic field along the z direction. Okay. So, and this RH is basically 1 by M2, N is the carrier density and Q is the charge. Okay. So, it can be E plus minus E. Okay. So, uh, so in case of N-type or metal, so Q is basically E, electronic charge, and it will be minus sign, so RH, the sign of the RH will be negative. When it is P type, so N will be uh, whole charge, okay, charge of whole, so it's equal to the electronic charge, but positive sign, so RH will be positive. So Hall coefficient is positive, corresponding Hall voltage will be positive for P type carrier, and for N type carrier, Hall voltage will be negative. Okay. So, from the sign of the Hall voltage, one can decide, one can tell which type of semiconductor it is, whether it is N type or P type. So how this formula has come? So basically, this you know that Lorentz force, FL Lorentz force is equal to Q E plus V cross H. Okay. So in electric field and magnetic field, what is the force acting on the charge carrier? So that is the Lorentz force. So due to electric field, Lorentz force is QE. So now, due to magnetic field, the force is Q V cross H. Now we have chosen this V. What is V? This V is basically not voltage. This V is the velocity, brief velocity of carrier. Okay. When this electric field is applied along the x direction, so current will flow along the x direction. That means the carrier will move along the x direction. It will have the velocity. So that is called drift velocity. Okay. Other drift velocity and velocity, there is a difference. Without any electric field, this velocity of carrier will be scattered in different direction. Now, when we apply electric field, they will be channeled in one direction. Okay, so that velocity in that direction is basically we tell drift velocity. It is directed in a direction. So there will be velocity along the x-axis. So that is Vx, that is V, and if magnetic field along the z direction, so due to magnetic field there will be force on that carrier along the y direction, right? This is B cross H. So if it is x direction, H is z direction, then this force will be along the y direction. Okay, along the y direction. So due to this force, so now again it depends on the sign of the charge. So in case of hole, whatever the direction of the force, for electron it will be in opposite direction. So whatever the carrier inside the uh, sample, so this ball will be shifted say along this direction, and then electron will be shifted the other direction. Or if it is in case of metal, only one type of carrier is there. So when electron will be shifted along this direction, this other direction, other surface of the sample, so if there will be lack of electron, only positive charge will be there. So equivalent positive charge will be in this, if it is in this surface, so other surface will be populated with the negative charge. So there will be separation of positive and negative charge, just like battery. So there will be a voltage along this. Voltage will develop along this y direction. So this voltage is basically Hall voltage. Okay. So here you know that electric field along the x direction current is flowing. Okay. So due to voltage, due to electric field is Ex along the x direction. It is not whole electric field. It just electric field for constant current passing through the sample. So Ex now this length x, this length if it is x, so Ex into x, that will be Vx voltage. So voltage along the v direction, along the x direction Vx. Now Jx current density along the x direction, that is equal to sigma Ex. Sigma is the conductivity. So so Jx equal to sigma Ex equal to N-Q-Vx. Okay. So current density is basically N-Q-Vx. So this Vx is velocity, deep velocity of electron of carrier, and this Vx is the voltage. Capital Vx is the voltage. So this is the relation. This is the relation. This general relation for between electric field and the current density. From there, you can basically connect with the current and the voltage, because current is basically current density into the cross-sectional area. So in this case, cross-sectional area is Yz. This is the cross-sectional area Yz. So multiplied with the J, that will be current I, and voltage, you know this, electric field into this length, that is the voltage. So this you can express in terms of voltage and current also. So here you see this. Now what happens, that due to Lorentz force along the y direction, that is Q Vx Hz, Q Vx Hz. Okay. So this force, due to this force, electron or carrier will move in y direction. When they will move, so there is a charge separation. Due to charge separation, that voltage will develop. When voltage will develop, then this charge, due to this voltage, it will be affected. It will feel force due to the voltage. Due to the voltage or corresponding electric field, so it will feel the force. That force is basically QEY. So EY is basically here electric field produced, developed along the y direction. This is a whole electric field. Okay, so the same charge will feel force. Due to the Lorentz force, this electric field is along the y direction is developed. Due to that electric field, again this force, this charge carrier will feel the force in opposite direction. So there will be balance between these two opposite force. One due to the whole electric field, and another is due to the Lorentz force because of the magnetic field. So this is Lorentz force due to the magnetic field along the y direction. This force will be balanced due to the force due to the due to the force coming from due to the force coming from the Hall voltage or Hall electric field along the y direction. So that is U E Y. So this is the force Hall force FHY along the y direction. When FLY will be equal to FHY, so that time it will reach to the equilibrium, and from this from this equation you can find out EY, Hall electric field equal to Vx Az. Now VH is basically Hall voltage, again electric field, Uy into this length, that is Y. So that will be Hall voltage that equal to Ey equal to Vx Hz into this Y. So from here I can write this Vx equal to Vx equal to, you can write Jx by Nq, Jx by Nq Hzy. So now Jx I can write in terms of Ix. So multiplied with this, so Jx I have written Ix by Yz, Ix by Yz. So Yy will go, and Ix Hz by Z into 1 by N2. So Hall voltage will get. So 1 by N2 is RH, then Ix Az, and I think RH. Now here there will be another parameter, that is J. I think it will be there. Okay. So Ix Az by Z into 1 by N2. 1 by N2 is RH, so RH. Okay. So from this expression, as I mentioned, that this Hall voltage will depend on the Ix current, constant current going to the sample along the x direction. So this Ix generally we keep constant. At a optimized value. It cannot apply very high value because I think there will be heat due to this current. So heating of the sample will change the parameter. So we will avoid the heating of the sample. So Ix will keep in small value, optimized value, so that without generating heat, we can do the experiment.
Now, Z also is the sample geometry. Z also is the sample geometry. So, for a particular sample, Z is constant. Now, this if Ix is constant and RH, Z RH is carrier density for a particular sample, carrier density is constant. So, RH is constant. Okay. So, VH will be proportional to Hz. Okay.
So, if you do the experiment just measuring Hall voltage as a function of magnetic field, then for a particular current, so then you can plot pH as a function of H, then it is expected that it will be linear curve of pH versus Az. So from that curve you will get slope, and that slope will be equal to the RH Ix by Z. Okay, Z value is known to you, and Ix also known to you. So pH you are measuring, experimentally you are measuring, so you will get the RH. So if you get RH, then you can find out the carrier density. You can find out the carrier density. Okay. So I will come later on about what are the how to find out the parameters. So this is the basic theory of this Hall effect. So note that in general this Hall voltage VH equal to RH by IX, RH into IX into AZ divide by Z, that's DC. So is not linear function of magnetic field of AZ. So according to this formula, it is expected that it will be linear, uh, but it is not linear in general because the here if RH is constant, then only it will be linear, but RH, this whole coefficient is not constant but a function of magnetic field. So this coefficient, Hall coefficient, it is not constant in general. It is a function of magnetic field. So that means RH will also change with the magnetic field. So that's why. So you may not get the linear function. So if it is not exactly linear, so you should not be worried. But if it is not linear, there is no problem. You just for a particular on the curve for a particular point, so you can find out the slope, and from that slope, for that magnetic field, you can find out the RH and corresponding parameter. Okay. So, however, our derivation is based on assumption. So, why RH is not constant? Reason is that all carriers in the sample have the same dip velocity v. So that we have assumed. We have assumed that all carriers will have the same dip velocity. But it is not the case. Because velocity have some distribution and dip velocity will not be same for all carriers. So if they are not same, then basically because of that this RH will be field dependent, electric field, magnetic field dependent. So but here we are treating as a constant and expecting that we get the so this formula is basically based on this assumption. Because of that it looks RH is constant, but it slightly varies with the magnetic field, and reason is that the dip velocity of all carriers are not equal. But we have considered equal, so that's why this formula is linearly dependent on the magnetic field. All voltage linearly dependent on the magnetic field, but in reality there is slight difference. So the difference due to the variation of the dip velocity, and so one needs correction of this formula, but we are not going to do that. We will use it assuming that this all velocity will be dip velocity are same. So that's why from the linearity it will slightly vary. So if you experiment, if you get not exactly linear, so you do not need to be worried. So why it is not exactly linear? It is deviated from linearity. So that reason you know because of the variation of the heat velocity. So now, say for one type of carrier sample, if you take metal or N-type semiconductor or P-type semiconductor, then if you then RH equal to 1 by N cube. Okay, so sign of RH depends on the sign of Q, as I already told. Okay, and VH equal to RH IX HZ by Q by Z. Okay, so for a fixed current and HZ, VH is proportional to 1 by N. Okay, VH is proportional to 1 by N. So now RH equal to mu by sigma. RH equal to mu by sigma. So as I showed you, so measuring RH and sigma, one can also find out the mobility. So this expression are telling that these are the parameters. If you do experiment, you can find out sign of the carrier, concentration of the density of the carrier, just measuring Hall voltage. From there, Hall voltage is a function of magnetic field. From there, you can calculate find out the RH. If you find out the RH, then you will get sign as well as the electron, not electron carrier density. And if you measure RH along with conductivity or resistivity of that sample, then you can find out the mu mobility. In this case, so hole will contribute in the mobility. Sorry, in Hall voltage, as well as electron also will contribute in the Hall voltage. But this Hall voltage for hole and electron, so they will be in opposite direction. Hall voltage will be in opposite direction. In one case, this is a positive direction. For other case, it will be in opposite direction. So basically, uh, contribution from these two carriers in Hall voltage will be in opposite side, okay, and their contribution of Hall and contribution in Hall voltage from electron and from hole, they are not same. There will be weightage. There will be weightage in contribution of hole and electron. If you consider this weightage, so considering the weightage, so weighted average from hot voltage, you know this RH, Hall coefficient for such sample is can be written as RH equal to mu A square P minus mu Z square mu E square N divided by Q mu H P plus mu E N whole square. Mu is the mobility, P is the whole concentration, N is the electron concentration, Q is the charge. Okay. So this one can find out, derive this formula. So check if it is one type of carrier. So either n equal to 0 or p equal to 0. If n equal to 0 or p equal to 0, just consider this term will go, say n equal to 0, this term will go. So mu A square p divided by q mu square h p square. So mu square h will go p and this is p square, so there will be 1 by p q, okay, or 1 by n q, okay. So this q is all the time it is positive we have considered, so this negative side will come in case of electron, and positive sign will come in case of hole, okay. So your RH will be either 1 by PQ or minus 1 by NQ. Okay. So we are getting the same formula as we have seen for the derived for the one type of carrier. So this formula that we checked that it is fine. Now here you can see that contribution from both carrier. Okay. So P and N are, as I told, density of hole and electron, miniature mobilities of hole electron. Now, this RH, not RH, this mobility is very important parameter in semiconductor. So, mobility of electron and hole, they are not same. Mobility of electron is higher than the mobility of the hole in semiconductor, and they are they are they are not constant but function of the temperature. So with temperature, this mobility affected a lot. Okay, its mobility varies. So that's why earlier I told this mobility. Earlier I told this RH is not constant. Reason is that magnetic field with temperature it varies. And reason of variation is, as I told this, that deep velocity are not same. Okay, deep velocity are not same at all magnetic field. So their deep velocity, here I am telling in terms of mobility. Basically, mobility is defined by the deep velocity divided by electric field. Okay. So per unit electric field, what is the mobility? What is the deep velocity? That is called mobility. Okay. So basically, deep velocity and mobility are same, except that in one case this is per unit electric field. What is the velocity? That is the mobility. Okay. So now this mobility is very sensitive to the temperature. With temperature it varies. Okay. So in case of, here you can see contribution. So mu H is generally less than mu E. Okay. So this term will be higher than this term for in case of intrinsic semiconductor. If P and N are same, but hole mobility is less than the electron mobility, so this term will dominate. Okay. Now, in case of P-type sample, so if P is greater than N, in that case, what will happen? This term is higher. This term will be higher than this term. Okay. Now with temperature, as I told, with temperature, this term will dominate. This term will dominate. Okay. So because this mu E, that will uh, with temperature initially this term is greater than this term, so it is RH is positive. Now with temperature, so this mobility will decrease. In both cases, mobility will decrease, so this term will decrease, this term will decrease, and this negative term also it will change. So this resultant term basically uh, for room temperature, whatever the value, it is positive. Now with temperature, what will happen? This value will decrease, this value will decrease, this value will decrease, and we get basically inversion of this coefficient RH. Hall coefficient inversion means from positive side to negative side change. So it will pass through the zero, RA is 0. So in that case, when RA becomes 0, in that case, what will happen? So this term will be equal to this term. So from there you can get the mobility ratio of hole and electron in terms of the carrier concentration ratio. Okay. So Hall coefficient versus the magnetic versus the temperature, or Hall voltage versus the temperature. If you measure the Hall voltage as a function of temperature, then from there you can find out the mobility ratio of the electron hole of that sample. Okay. So basically, what are the experiments we can do, or what are the important characterization of the sample? So important characteristics are of that inversion curve. So from there, basically, you can find out the mobility ratio and the mobility ratio or the carrier density ratio. So measurement of RI is a function of P. For P type semiconductor, the ratio of mobilities of hole and electron can be obtained. So this is one characteristics of this Hall effect. So second is Hall coefficient for one type carrier as a function of magnetic field. So that basically follows this as I mentioned. So measuring of RH as a function of magnetic field gives carrier density type of carrier, right? As I described. And since RH equal to mu by sigma equal to sigma is 1 by rho, so rho mu. So measuring resistivity and Hall coefficient mobility of carrier can be obtained for one type of carrier. Okay, so one can find out the mobility if you know the resistivity of the sample, or if you can measure the resistivity of the sample. So combination of the measurement of Hall coefficient or Hall voltage and the resistivity or conductivity of the sample, one can find out this carrier density, type of carrier, and mobility. When one type of carrier, and for other case, you can find out the mobility ratio if both carriers are there. You can find out the mobility ratio, especially in case of p-type silicon. Okay, so our experimental geometry, for this Hall effect experiment would be like this. Would be like this. So you will have a sample. Okay. So this connection in Hall geometry, this connection is there will be two probe for current and two probe for measuring the Hall voltage. Okay. So in case of magnetized resistance measurement, we have used linear probe method for measuring the resistance, linear probe method measuring the resistance. So for measuring the resistance, so basically another way to use the probe, that is also probe, but that is called Van der Waal geometry. Van der Waal geometry. So they are basically the probe are put like this. Probe are put like this. Okay. So so all are not linear on same line. So they two are in perpendicular to the other two. Okay. So these two are perpendicular to this other two. So this here I have shown this Van der Waal geometry. So four probe 1, 2, 3, 4. Here I put this way. Okay. So this four probe Van der Waal geometry, the advantage is that this one you can use for measuring the resistance as well as for measuring the Hall voltage or Hall coefficient. So Van der Waal geometry gives us facility for measuring both resistivity and the Hall voltage, Hall coefficient. So when you will measure the Hall resistivity, so then we use is parallel this this these two probes if we use for current, so these two probes we will use for voltage. So it is in same line, so parallel. The I and B parallel. And for Hall geometry, so you will use this if these two probes are used for the current, so this other two and 4 will be used for the voltage measurement. Okay, so this they are perpendicular. So I and B perpendicular. Okay, so these are so that mode can be used for. So the externally just image you have 4 probes now. Which two probe will be used for voltage and which two probe will be used for the current? So that you can decide externally. Okay, so Van der Waals geometry is useful for the measurement of the resistivity as well as the Hall effect. So, but only linear probe that you cannot use for the for measuring the Hall coefficient. Only you can use for the measuring the resistivity or resistance. Okay. So, but in case of Van der Waals, so this different formula is used for resistivity measurement. So Van der Waals formula is called E to the power pi RT by RS plus E to the power minus pi RH by RT equal to not RS. So RS is called the sheet resistance, and one can derive this formula. RS equal to pi R by log 2, natural log 2. Okay. So this R is the resistance. So basically, from this formula you can see if you can measure the RV and RH. What is RV? RV is vertical resistance. When you are using vertical column, means this way, these two probe for current, these two probe for resistance, voltage, or vice versa. This for voltage, this for so vertically when you are using. So in that case, you calculate the from the measuring voltage and current, you can calculate the resistance. So there is basically we are using RV and RH is in horizontal. So these two you are using for current and these two voltage or vice versa. Okay, from there this current and current and voltage in horizontal direction. So whatever resistance you are getting, that is RH. Okay, so this is easy to measure. So if you measure this one, so from this formula you will get RH. Now using this formula you will get R. So when you get R, so you can calculate the resistivity or conductivity. Okay. So anyway, we are not going to use this one, but I just told you that generally in research, generally we adopt this Van der Waals technique for measuring the voltage, for measuring the resistivity as well as the Hall coefficient. So, but in our lab we use just different linear probe method for measuring the resistivity, and this Hall geometry we use this way for measuring the Hall coefficient. Okay, so what you need to do? You need to do experimental data collection. So that experimental data collection is basically you need magnetic field. You need magnetic field. So calibration of electromagnet, that is common. So magnetic field versus coil current, that one has to do this experiment and plot it. Then you will get calibration curve. So from coil current you will be able to tell what is the magnetic field. Then next data you have to take, that is Hall voltage versus H magnetic field. Okay. So basically we use coil current, and from this calibration we will get the magnetic field. So for constant Ix and T temperature. For constant current and for a constant temperature, a particular temperature, room temperature, we'll do this experiment. We'll measure the Hall coefficient as a function of Hall voltage as a function of magnetic field. Now, if you plot that one, then from the slope, we'll be able to find out the RH, and from RH, we'll be able to find out the carrier concentration. And data for resistivity, for resistance measurement, one can do the resistance measurement using the Foot method, or this resistivity will be supplied for that sample. So from there, you can find out the mobility of the carrier. So data for RH as a function of temperature and find out inversion point, okay, where RH will be equal to 0, and from there one can find out the mobility ratio. Okay, so we'll demonstrate experiment based on this theoretical analysis. So let me stop here. Thank you. Ix and T temperature. For constant current and for a constant temperature, a particular temperature, room temperature, we'll do this experiment. We'll measure the Hall coefficient.